Anya.
Good afternoon, everybody. Welcome to this meeting. I will read my land acknowledgement to start off this meeting. I'm so glad that we are able to gather today. It's wonderful to bring everyone together to do this important work. But before we start, I would like to make some acknowledgements. We are meeting on land that has been occupied by humans since the glaciers retreated over 10,000 years ago. I want to acknowledge those first people. We are meeting on the land that has been home to various nations over these thousands of years. I want to acknowledge the Anishinaabe, Haudenosaunee, and Chinangtan nations. These are the first nations of this land. We are meeting on land covered by the Dish with One Spoon Wampum, which states that anyone that takes up residence in the Great Lakes Basin, as we have, owes it to everyone else to share the resources and not deplete them. We are meeting on the land covered by Treaty 45 and a half, the Saugeen Treaty, signed in 1836. I acknowledge that our presence here is governed by this treaty and call upon our government to honor it. We are, if we are non-Indigenous, immigrants and settlers, as I am an immigrant. The true history of this land hasn't been taught in our schools, and we have much to learn about the true relations between the Indigenous people and Canadians. I acknowledge that I am on this learning journey and invite you to learn with me. The Indigenous people cared for this land and practiced sustainable living so as to not destroy the environment. We have much to learn from their teachings, and I wish to acknowledge what a deep privilege it is for us to gather here. As part of our reconciliation work, I wish for stronger ties to the Indigenous nations we live alongside today. And by the way, so I am Anya van der Vlies. I am the co-chair with Bill Knoll of Protect Our Waterways, the local group here in South Bruce that are fighting the geological repository proposed for our community. I hand it over to Bill.
Thank you, Anya. Well, thank you all for attending. I hope this session proves to be worthwhile for those attending and that we can learn something from the webinar itself. We are fortunate to have three excellent presenters tonight or this afternoon with us, and we'll introduce them later. What we plan to have is a kind of a panel discussion. We'll have a 5-minute introduction by each one of the presenters shortly, and then we'll go into some questions that have been pre-prepared for the panelists to answer, and then that'll follow by questions from the attendees themselves. So I'm going to start off with asking Cindy to do her presentation. But first of all, I should give you a little background on Cindy herself. Since joining Beyond Nuclear in 2007, Cindy has focused on iodizing radiation in health and its impact on health and the environment from both a scientific and a historical perspective. She advocates for the fully protecting the health of females and early the stages in the face of uncertain health conditions. She earned an MS in environmental science from the Johns Hopkins University. So Cindy has a short video that she'd like to play. So let's start with that, Cindy.
Okay, thank you, Bill, for that introduction. So Anya, I think you were going to... Thank you.
Well, let's move to a new website, Anya. Good.
I'm not hearing any sound. Nuclear power releases radioisotopes into our air and water. Sometimes a lot of radioisotopes are released from nuclear power catastrophes like Chernobyl in Ukraine or Fukushima in Japan, contaminating many hundreds of miles. But you don't have to have a nuclear catastrophe to release radioactivity. Radioactive substances are released from nuclear power even when we use it as intended. People living miles out from a nuclear power facility can be exposed. Women and children and pregnancy are especially susceptible to risks of exposure to radiation. These substances can collect in our bodies, exposing us to yet more disease risk. So let's look at where some radioisotopes from nuclear power can collect in the pregnant body. Radiocesium, a potassium analog, collects in all muscle, including the heart and the fetus. Pathology samples of children around Chernobyl indicate radiocesium uptake in the thyroid as well, although this is not an expected or officially recognized outcome. Radioiodine is a radioactive form of stable iodine, which is collected by our adult and fetal thyroids. Radiocrypton and radioxenon are gases that are fat soluble and are absorbed by fatty tissues. Radiocrypton collects in the adrenal glands, while radioxenon collects in the liver. It should be noted that the brain is 60% fat and the fattiest organ of the body. Radiostrontium mimics calcium, a basic building block of the human body, and like calcium, it collects in bone, more in females than males. It also collects in the ovaries and the fetus. Once radiostrontium lodges in the mineral bone of growing skeletons, it likely won't leave for most of that person's life. Uranium is the fuel that runs nuclear power reactors. Uranium collects in bone, liver, kidneys, placenta, and fetus. Radioactive carbon and radioactive hydrogen, called tritium, collect throughout the whole body and can collect in fetal tissue at twice the concentration as they do in maternal tissue. This is because they are basic building blocks of the human body. The digestive tract will get exposure from all radionuclides ingested, and the lung will get a dose from inhaled radionuclides. What I would point out from this graphic is the collection in the fetus of nearly every radionuclide presented in this list to the left. Exposure to radioactivity from nuclear power is associated with a number of cancer and non-cancer diseases, particularly in children. These include impaired neural development, heart problems, as well as other non-cancer impacts. And most cancers, particularly leukemia and central nervous system cancers. Okay, thank you, Anya, for playing that. I just want to add to this the concept that at this point, we are a number of generations into the nuclear age. And so as the video implies, by having a pregnant woman, we are now dealing with multi-generations of exposures and any accumulating damage that may be across those exposures. And so it's important to remember that at this point in our history and in our humanity, we are continuing to expose populations that have legacy contamination and legacy exposure issues. So I'll stop there. I wanted to throw that out as a sort of an overview concept.
Thank you, Cindy. Next, we are going to Dr. Ian Fairley. And Dr. Ian Fairley is a citizen scientist interested in radiation issues. He's a Canadian. I don't know why he's living in London, but he is. And he went to high school in Sarnia, and his first degree was from Western University in London, Ontario. He has degrees in chemistry and radiation biology, and his doctoral degree was obtained at Imperial College in London and was on nuclear waste policies. He was the chief scientist advisor to the British Government Committee on the Radiation Risks of Internal Emitters. He is a consultant to NGOs and to nuclear advisors both in Europe and North America. So, Ian, over to you.
Thanks very much, Bill, for that very kind introduction. I guess I want to stress that I'm a radiation biologist. And I want to get across that we all should be very wary of exposures to radiation for two main reasons. And the first reason is that the nuclear establishment really only talks about one kind of radiation, that's external radiation. And as Cindy has very aptly pointed out in her diagram of a woman and the various body organs, it's the internal radiation that is a serious matter. And if we're having the proposals for a nuclear waste dump at South Bruce go ahead, that's the major way that radiation will get inside us. In other words, it will be internal radiation, not external. The second point that I want to get across is how to explain why cancers arise from radiation. This is sort of very basic cell level stuff. But the smallest dose of radiation you can get, the very smallest, is when one track of radiation goes through a cell, in particular a cell nucleus. Thus, you can't get any lower than them. And yet we know that there's a finite chance that a cancer will arise from just that dose. In other words, one track through one cell nucleus. The body consists, average-wise, about 6 billion cells. And so it only takes one track to go through one cell, and then bingo, you have the start of a cancer, of a tumor. Because what happens is that the radiation transforms the DNA in the cell and effectively mutates it so that when the cell reproduces, it makes a clone which is deficient or which is badly formed or which cannot recognize its neighbors. And that what happens is they keep on reproducing. You get a mass of cells which are cancerous, which is called a tumor. Now, that very, very basically means that one radiation track through one cell, bingo, you've got a cancer. Now, I'm not saying that happens in every single track through a cell, but the probability arises that it could. We call this stochastic. It's a jargon term meaning that the probability exists. It's the same kind of thing that would happen if you smoke a cigarette. Smoke a cigarette, the chances of you getting cancer from that cigarette are low, but it's not zero. You could get a cancer. A good friend of mine in the United States, Jan Beya, from Princeton, put it this way. He said that if you smoke or if you get a radiation dose, you get a negative lottery ticket. Like going down to the local shop and buying a lottery ticket. Except this time, you don't win, you lose. You get a cancer. In other words, it's a matter of fate, a matter of chance as to whether you get it or not. Now, what does that mean for you and I, for the 70 people who are listening in? It means we should take steps to avoid any exposures to radiation, if possible. The reason being is that it's not good for you. In the Western societies, for reasons we don't really know, the incidence of cancers is steadily increasing all the time, ever since the 1940s. And we're not really sure why that is occurring. You could say that we have an aging population, but that's always been going on. The really worrying thing is that the incidence of cancer in children is increasing too. I had to write a paper about that. And much to my surprise, I found that and both, well, in most Western countries, that the incidence of cancer is increasing among children. By that, I mean under the age of 12. So I'm hoping that the information that we're going to be providing, and also by answering our questions that are going to be posed to us, that we can, how would I put it, provide information to everybody concerned to increase our awareness of the dangers of radiation and to redouble our efforts to make sure that if you don't want it in South Bruce, you don't have to take it. And I'll be providing very good evidence to support that contention. Thank you, Bill. Bill, we can't hear you.
I always turn
okay,
off
well,
the mute button. So sorry about that, but thank you very much, Ian. Some very insightful thoughts that I'm sure will raise some questions from the attendees. So we're going to now turn over to Mary Olson to do her brief introduction. Mary was raised and educated as an evolutionary biologist. In 1991, when she joined the staff of Nuclear Information and Resource Services, applied her concern for the future generations to becoming an educational resource and policy advocate and an ally for communities impacted by nuclear waste. Mary retired from NIRS in 2019 and founded the Generation and Radiation Impact Project, a nonprofit educational organization based in the United States. So Mary, I'll turn it over to you for your brief introduction.
Thank you, Bill. And thank you everyone who's here today and for your interest. And I too stand ready to help people understand, because radiation has the ability to affect us, but the future generations come through us. And so indeed, this generation is the gateway for all the other generations that will follow. And radiation has the potential, as Cindy's illustration shows, to affect the unborn child, the developing fetus. And a point that I will add to Cindy's presentation is that if that's a female fetus, her ovaries will develop before she's born, and every single egg that she will ever have is formed while she is in her mother's body. So those eggs that may in the future become children were formed in their grandmother's body. So right now, pregnant women are literally 3 generations of people being affected by the decisions made in every community about radiation, because radiation can impact that pregnant woman and therefore impact her grandchildren at the same time. I'm going to briefly share some slides because my organization is actually called Gender and Radiation Impact Project. And I want to talk now about, this is, let's do the share, the big thing. There we go. This is what Ian was talking about a moment ago. I'm going to move fairly quickly because we said 5 minutes and we're going to keep to it. But Ian was talking about tracks. So on the left side of this slide, there's squiggly lines with an arrow. And each one of those is a single energy external gamma or X-ray type exposure. And then you see the little circle with the nucleus in the middle, that's a cell. And radiation impacts our bodies at the level of cells. This is what Ian was talking about when he said tracks. Each one of those squiggly lines is a potential track if it makes it in and through that cell. Then we have the highlight in the middle, which is really where cancer occurs, is changes to our DNA is what may over time become a cancer, but it might also be repaired, not in the case of a double break, but if it's a lighter form of damage, it can be repaired by the cell, or if it's so catastrophic, the cell may die. So I'm reinforcing the idea that not all damage becomes cancer. But if you have damage that allows the cell to reproduce abnormally, that's what may also, there's other factors that may or may not allow that cell to live long enough to produce a cancer. But if it does, it's out of control cell reproduction, which is what Ian was saying about having a clone situation. So when I started this work, I was educated by people who were in the industry, people in academia, scientists, et cetera. And the idea back in 1991 was that radiation was indiscriminate. If you had that process that I just showed you on the previous slide, it would come out the same no matter who it was getting the radiation dose. So it wouldn't always have the same outcome, but the radiation and the chances and the probability and all those things would be the same no matter who was getting exposed. Well, I already knew that children were more susceptible to radiation, and a lot of other people already knew that at the time. So there was already a little wiggle in the walk. But nobody was saying that there might be a difference between boys and girls back in 1991 as a day in, day out point of view. In the early 2000s, someone asked me that question. Was there a difference between boys and girls? I couldn't find an answer. My mentor, Dr. Rosalie Bertel, said, Mary, go look at the data. I really complained about that, but I finally did it. And the data shows from the largest data set ever, which are the people in Japan who survived the US nuclear attacks at Hiroshima and Nagasaki in 1945. They are first generation, and the only type of radiation looked at is that one that Ian said that the general discourse on radiation is about external exposure. That means X-rays or gamma rays. So this is gamma rays, and these are people in 1945, but the age of exposure was tracked in the big study of them. And the people who over 60 years came out with the most cancer were the people who were young children. And this is all adjusted for lifespan and et cetera. So children are more impacted by radiation. But the big shocker is that in that group of youngest people from birth to 5 years old who were exposed to the A-bombs, we find that for every boy who grew up and over 60 years of tracking got cancer, and boys did get cancer, twice as many girls got cancer. So in my slide, I chose to say 2 versus 4 rather than 1 versus 2, because I could put more diversity into my silhouettes. But it's a 1-to-2 ratio in this age group. When you look at the adults, and that was incidence of cancer. This is now people who died of cancer. For every 2 men who died of cancer exposed as men over the age of 20 on up into their 40s, this is all bigger group, 3 women in that group of exposure. The age of exposure is what we're looking at, and then the biological sex. 3 women died. And that actually changed my own behavior in the field. So I'm hitting my time. But I want to end with this picture because this is a summation of the data. I'll just quickly tell you that I got it all out of this big report from the National Academy of Science. I did not go collecting data, but this is a summation of that data based on the age people were in 1945 when they were exposed. This is a scenario that says, what if they all got the same level of radiation so that we could more easily look at age of exposure and biological sex? And you can see that in every group of age, females got more cancer over 60 years than did males, but that the difference is biggest when the exposure is in the early childhood. But the final thing I'll say is we're not looking here at childhood cancers. We're looking at total cancers over 60 years. So you can have adults walking around who were not exposed to children and they have a lower probability that they're going to get cancer, or you can have adults walking around who were exposed in this youngest age group and they have a much higher chance of getting cancer compared to those who were not exposed till they were adults. Which becomes the big message I'm ending with, which is we must protect the children. So don't think about that money as only being benefit to the children. Think about the potential for radiological harm as well. Thank you.
Thank you, Mary. Very great. Great slides, great visual indications of how people are affected by cancer. We're going to move into the next phase of the webinar, and we're going to ask a number of questions to the panelists, and then we'll open it up to the attendees to ask questions. So the first question is going to go to Sydney, and the nuclear establishment suggests that below the threshold of 100 millisieverts, which there are no I'm tongue-tied, no statistically scientific observations of cancer or other health impacts from the exposure to ionized radiation. This is a statement from the nuclear establishment. So, Cindy, what I want you to do is, how would you respond to such an argument when addressing non-scientists or members of the public or these people who are attending today, who may not understand the finer details about the statistics or the epidemiology of the disease itself? So, Sydney, can you turn us on to some ideas about that?
Sure. So I think you're talking about statistical significance is one of the issues that they bring up a lot when they're talking about studies. I will start answering this question, but I'm going to also pass it on to Ian and Mary because I think that there's a lot to unpack here. There are a lot of assumptions in this question that are actually false. So I'm going to start with the statistical significance piece. Statistical significance is a test, and it's meant to be a test that's used to determine how much a health finding may be due to pure chance. So when you get a bunch of disease in a community, is that due to just bad luck, chance, or is it due to something in the community that is making people sick, like radiation? Well, the problem arises in radiation health studies when they do find health impacts. They often arbitrarily will set this statistical significance test at what I'm going to call a much higher bar. And when they do that, it erases the health impacts that they actually did find. And so you get studies that say, we didn't find any health impacts on X site. But when you look at that site, when you look at that study, you say, well, actually, they did find increases. It's just that they didn't meet their own test of statistical significance. And since they decide what that test is, or what the level of that test is, they can decide that they're going to set it at a level where these diseases basically won't matter. Now, this has become such a problem in scientific study that scientists have advocated abandoning statistical significance in certain instances in health studies because it has been erroneously used, not just in the radiation health studies, although it does seem to be quite widespread in those, but other health studies as well. And they use it to erase critical and genuine health impacts. So I will put the link to that study in the chat, but I also want to point you to a book that Ian Fairley and I collaborated on. It's The Scientists Who Alerted Us to the Dangers of Radiation. And this is the cover of the book right here. There's a really good appendix in the back that talks about this very issue, Appendix F, misuse of statistical significance tests in health studies. And the reason that I'm going into a little more depth here than I normally would is because this is one of those things that masquerades as science. And if you use it correctly, it is science. And if you use it incorrectly, which they can do, it misdirects your attention. It hides things in the data that are there. And so it's very important for people to understand that whenever they see the words statistical significance in a health study, they really need to closely examine the data in that study to see if there actually were increases in health impacts. Because just because they're saying something isn't statistically significant doesn't mean that there weren't health impacts. In fact, there probably were. The final thing that I would say is if it were up to me, I would go back to all of the radiation studies and redo them on the basis of what their bar of statistical significance was and see when they actually become statistically significant and then talk about the incidence of disease that they find in those studies based on that. But that's a hope and a dream of mine. I'll turn the question and the rest of the question over to Ian and Mary now. Mary, do you want to go?
Yeah, I just have a brief addition, then I'll cede to you, Ian. But I've spent quite a lot of time reviewing current papers on radiation impacts to write a paper to update on the differences between males and females. And I can tell you that a very large portion of the radiation literature is of studies of radiation exposures well below 100 millisieverts, which is where we started with this question. They assert in the question that there is no health effect or no statistically significant health effect below 100 millisieverts, which is a darn high dose. The literature has plenty of health effects that are statistically significant way below 100 millisieverts. So Cindy said that, and was correct to say that there are assumptions in the question that are just plain incorrect. So it's incorrect to dismiss radiation below that level, and it's incorrect to assert that there isn't a huge body of research out there that substantiates statistically significant findings well below that level. For cancer, for heart disease, for reproductive impacts, I mean, across the boards, you do not have to go to that level to find them. Ian.
Thank you. Ian?
Yeah, sure. As Cindy said, there's a lot to unpack in the question, particularly just about statistical significance. For a lot of people, it throws a wobbly at them because they think the word, because it's not significant, they think therefore it's not, the findings aren't important or they're not relevant. Well, no. Statistical significance does not mean that at all. It's a jargon phrase used in statistics. That's all, a jargon phrase. And it means that if the results of the findings don't meet our imposed bar, then we're going to throw all the results out. We're going to throw the baby out with the bathwater, in effect. And as both Cindy and Mary have said, this is an example of bamboozling ordinary people who really don't know anything about this. But we can tell you quite assuredly that there have been many, many instances of epidemiological studies which have concluded there definitely is no raised incidences of cancers, thyroid cancers, or leukemias, or whatever. And when you look at the study, it's black and white that there were increases. But they said, but they weren't statistically significant. Well, that's a lot of baloney. Interestingly, I'll give an example of this. About in Ontario, about maybe 10 years ago, I think it was, Pickering made an application to extend its operating license. And I was asked by an agency, an NGO called SILA, to prepare evidence against this, and I did. And in particular, I looked at all of the epidemiology studies into increased leukemias near nuclear facilities only in Ontario. I'll repeat that. I looked into, I think there were 7 or 8 epidemiology studies in Ontario of raised levels of childhood leukemias near nuclear facilities. And in every single case, there were increases. But in every single case, the report said that there weren't, because the increases weren't statistically significant. Well, in a situation like this, you have to be, the scientists should be honest and say, yeah, these are the data, set up what the data is. And the data does show an increase, but it depends on whether we think this is significant or not, statistically significant. Well, what they should have done in these cases is lumped the studies together in a meta-analysis, but they didn't do that. Because if they had done that, they would have found that the increases would have been statistically significant. But of course, they don't want to see that. So this is manipulation of science in a gross way here in Ontario. And so I want to get across to everybody who's watching in that there are increases in childhood leukemias near nuclear facilities, all nuclear facilities, whether it's Pickering or Bruce or Douglas Point, on Gentilly, that's actually in Quebec, and that we should be worried about it. Now, I'll just finish off by saying this, that I emphasize a point that that Mary made. The question says that the nuclear establishment states that there are no observable levels of increase below 100 millisievert, exposures of 100 millisievert. Well, that's a lot of baloney. I'm sorry if I use an old-fashioned word. In a publication, you would say it's incorrect, but I would go further and say it's misleading. The point being that there are many, many, many studies which show increases all the way down to 2 or 3 millisievert, far less 100. So the question itself really needs to be reset and rejigged. By the way, just to finish off, a few years back, the BMJ, I think it was, British Medical Journal, brought out a landmark editorial saying that the whole concept of statistical significance should be junked because it was leading to wrong results. And we very much agree with that. I'll finish there, Bill, okay?
All right. Well, thank you very much. Those are some very interesting comments, and I'm glad that you have reasons why the nuclear establishment are making the suggestions that, you know, everything is safe no matter what the limits are. The next question is over to Ian, and it's the exposure limits for tritium vary differently from country to country. So why are there such variations, and how do the limits in Canada compare to other jurisdictions around the world? So Ian, do you want to take a crack at that?
Yeah, it's a good question. And why on earth does Health Canada have a limit for drinking water of tritium of 7,400 becquerels per liter, which is, well, it's bananas, to use a favorite metaphor used by the other side. Just simply crazy. If you compare it, say, with United States limits is 10 times stricter, 740. Compare it with Europe, it's 100. Compare it with states like Colorado and California, it's 15 and 18 respectively. So what on earth is going on here? Good question. Basically, in Canada, the kind of reactor that is used, CANDU reactors, put out a lot of tritium. A lot of tritium. They're the highest emitters of tritium in the world. Why? Because Canadian reactors use heavy water as a coolant. And that coolant, or as a moderator, sorry, and as a coolant. And as a moderator, it becomes extremely highly tritiated, and there are very high emissions, both to air and discharges to water of tritium in Canada, humongously high. So therefore, the limit has to be high. I mean, as simple as that. Because the technology is unforgiving and puts out very large amounts of tritium, you have to have high limits or lax limits, and that's exactly why it happens. I mean, we as NGOs ask ourselves a different question. What's going on here? Is it safe or is it not safe? Well, to be honest, a limit of 7,400 becquerels per liter is dangerous. And Health Canada should hang its head in shame at actually publishing a limit as high as that. Okay, I'll finish there.
Okay, thank you. Mary or Cindy, if you got anything you want to add to that?
Actually, yeah, I actually have a video on tritium per se. One of the things that it does is it talks about what the naturally occurring amount of tritium is, because sometimes you'll hear them talk about the naturally occurring amount of tritium, and there is, but it's minuscule amounts, even compared to, at least in the United States, the level that the EPA will allow us to be contaminated to. So they like to talk about tritium in the context of it being natural. Sometimes you'll hear this trope, but the fact is that naturally occurring tritium is in surface waters is so very, very much smaller than even what they allow the quote unquote drinking water standard or the surface water standard to be in the United States. So I can put the link to that video in here too. Yeah, that's all I had to say.
I want to add just one thing. Tritium is radioactive hydrogen. I think most people maybe know that. But the place that it travels around most easily is in water, either as liquid water or as water vapor. And so it very easily incorporates into any part of the human body. We are mostly water. And it's able to cross both the barrier that keeps bad stuff out of the brain, because water goes there, and also the placental barrier that's supposed to protect the developing fetus. So they don't just go to the brain. Tritium does not simply go to the brain and the fetus. It's that it uniquely has big access to those places that are supposed to be special in our bodies. And yeah, it also moves out. The industry loves to talk about, oh, it has such a short biological half-life, but believe me, it doesn't really matter how long if you get an exposure, that exposure has occurred. Thanks.
Thank you.
If I can add, Bill, if I can add,
Sure.
the most important danger about tritium is that once it gets inside you so easily, it sticks inside you in the form of organically bound tritium. Not just there for a few days. It depends. If it sticks to your carbohydrates, it's there for about a couple of months. If it sticks to your lipids, it's there for a couple of years. If it sticks to your DNA, it's there for your lifetime. So it all depends where the organically bound tritium is. And the half-lives, biological half-lives, vary according to where it sticks. It's dangerous stuff. The thing is that very rarely do we see any official publication which go into the detail about organically bound tritium and are honestly dealing with it. The nuclear establishment avoids it like the plague, but we should be looking at it. Anything that they don't like, we should be looking at, because that's where the dangers lie. So I'll finish there, Bill.
All right. Well, thank you. We're going to go on to the next question, and Mary, that's for you. And I know this is an area of interest for you. There are findings that radiation is more harmful to females and infants and young children than to adult males. So why is that? And I kind of covered this. And why does this matter for communities being exposed to radioactive releases? Does the way that nuclear waste is managed pose more risk to harm to women and to girls? So Mary, maybe you can give us a quick view of that since you covered some.
Sure. I want to start with the fact that the data I looked at is in the National Academy of Science 2006 report published and available online at no charge for a PDF download. So anyone can look at these numbers. And those numbers are, again, a first generation, no succeeding generations. And Cindy's right, we're well into 2 and 3 generations now. And external radiation only. So I can't, as a science committed person, I don't spend my days in a lab, so I won't say I'm a scientist, but I am definitely committed to good science methods and processes and conclusions. So I cannot assert that the radioactive contamination, which is one of our big, the water, the air, the food, all of those sources of potential internal exposure that we've been talking about, I can't say whether there's a biological difference there based on sex, male versus female. But I will say that in that case, it's dangerous for everybody and we should be protecting everybody. And I'm not really too worried about whether girls and boys are more harmed. We know children would be more harmed, but we don't really know whether boy versus girl is a factor there. So then the next question you asked is why? And my answer is we need institutions of excellence to have students and postdocs and principal investigators take up these questions from many different disciplines and find out. One hypothesis that is being supported by research is that female bodies have more reproductive tissue in compared to male bodies. Male bodies have reproductive tissue, but less. So that's a hypothesis, but it really doesn't account for the tapering off at puberty of the differences. So, more work is needed, and we don't have an answer to why. Why is biological sex a factor in radiation outcome? That question is worth a PhD and MD and at times as many as it takes to get the answer, right? So let's invest in that question. And then finally, about the radioactive waste. Well, I have spent some time thinking about the different phases because a radioactive waste program starts where the waste is now and ends with the waste in whatever the proposal is at its destination. But there's many, many steps along that way. And most of that way, workers are at the most risk of radiation exposure, but thankfully, we don't hire children for those jobs. I don't really know the sex distribution at this point to know male versus female in the exposure world of radioactive waste. So cleaving to the exposures to the public, the exposures that are most aligned with the case of external only gamma and neutron exposure, which is what the data I looked at was constituted. That's going to be during the transportation phase. That's going to be those big containers that offer some amount of shielding. You're not going to get a lethal dose of the gamma and neutron, but they can't shield them completely and also move them. They're just too darn big and heavy if you shield them completely. So there's allowable levels of gamma and neutron that is allowed to come through the wall of the container. Now, anything that's a contamination on the surface is on top of that. And those contaminations may actually be other types of radiation that we could talk about. But the gamma and neutrons coming through are the circumstance under which I would say female bodies are at a higher risk based on the data I looked at. So it's a low amount, but it's going to be ongoing, especially since this DGR is forecast to not only take all of the waste that currently exists, but any waste generated in the future. So that means that it's going to be ongoing for many generations, potentially, if nuclear is the choice of the people of Canada, which I hope they will begin to make new choices. But if not, the DGR will have generations of shipments coming along roads that impact many people, and along to the DGR community will get every single shipment. So the highest number of shipments will be at the DGR facility and the roads leading up to it. And all of those exposures mirror what the study that I looked at, the A-bomb survivors And so I would comfortably say that females are more impacted, but hey, stop a minute, because males are impacted in the first place. So it's not boys are safe, it's not men are safe, it's just their bodies, for an unknown reason, are somewhat more resistant. And female bodies, especially pregnant female bodies, are far more impacted. So I think that answers all of it, but maybe someone has something to add.
Thank you, Mary or Ian or Cindy, if you got anything to want to add there. I know.
Actually, I kind of do now because I'm reading Gordon's comment in the chat. And he says, with regard to tritium exposure for women and men, the Canadian Nuclear Safety Commission held a series of workshops on tritium exposures, and a scientist from AEC Limited presented evidence that women store about twice as much tritium than men do when exposed to the same concentration of tritium input, which I find interesting, because I've always done this with tritium and carbon-14 as basic building blocks when a fetus is building its body, as an outflow of pregnancy. But I asked Gordon in the questions, and maybe he can just answer me back, is this to do with just pregnancy? Or, because it sounds to me, Gordon, like you're saying this is women. So Mary, that's another thing to consider.
Share the site.
Sure thing.
Yes,
Science
Gordon.
has sites, CITE, share the site.
Okay. Well, let's move
All right.
on to the next question. Or were you finished, Cindy?
I'm finished. I just had to bring that up because that was a brand new thing to me, and we always like to add new knowledge to what we do, Mary and I. So
This is what it's all about, adding knowledge to people.
yeah.
So the next question is actually for you, Cindy. And this is another statement by the nuclear establishment, and I hear this many, many times. It says representatives of the nuclear establishment compare eating bananas or occasionally X-rays for medical purposes to exposure to radiation, suggests that they're the same and they're all of low risk. Can you explain how medical X-rays or potassium in bananas should be compared or should not be compared to the continuous exposures to radioactive emissions from a nuclear facility?
Yeah, we hear both of those tropes. The medical X-ray trope, I'm going to set aside for a minute, and I'm going to focus on the banana trope. It is worth noting that a small amount of potassium that occurs naturally in the environment is radioactive. It is also worth noting that potassium, both radioactive and non-radioactive, exists in our bodies in what's called a homeostatic state, meaning that the more potassium you take into your body, the more potassium flows out of your body, and your body will never have more potassium in it than a certain level. So right away, you may be subject, of course, to radioactive, naturally occurring potassium in your system from eating bananas, but it will never exceed a certain amount in your body. And it can vary based on individuals, etc. The difference is that when you intake a radionuclide, I'm just going to use cesium-137 as an example because that is a potassium mimic. That is in no way equivalent to potassium-40 because you collect that cesium-137 or 134 because your body thinks it's potassium. And it can put it in various different parts of your body, but it's not potassium, so chemically it doesn't act like it. So it can stay in your body and irradiate it. And then, of course, it's got a different specific activity, and there's a whole range. But when you take in any radionuclide, right, you are adding to your dose. I saw in the Q&A a question about naturally occurring radioisotopes, and it is important to remember that life on Earth could not evolve past a certain level of complexity until the background radiation dropped to a certain level, because nothing would have been viable. So here we are, through our use of nuclear technologies, spewing out the very substance that had to decay to a certain level before any of us as complex organisms could have evolved. And so when you ingest or inhale and take into your body radionuclides, you are adding to a body burden of naturally occurring radionuclides, and those naturally occurring radionuclides are also not safe, right? So you are compounding the potential you will be damaged when you add radionuclides that have been what I call man enhanced. So that means they're naturally occurring, but have been brought to the surface and spread around by us and our industrial processes, or they're radionuclides that we have created in nuclear technology facilities and spewed out to the environment. So all that is to say that, yes, there is a certain amount of damage that will come from naturally occurring radionuclides, but why would we add to that by spewing out more radionuclides into the environment and adding to our body burdens and the damage that it can cause? Right. Oh, and there was the first question, X-rays. Yeah, so X-rays. When you're in medical, when you're getting a medical exam and it's an X-ray, I'm not talking about any other kind of medical radiation exam. I'm talking specifically about X-rays. X-rays are generated by a machine, in this instance, for medical procedures. When you shut that machine off, your exposure is finished. When you ingest or inhale a radionuclide into your system, your exposure continues until either that radionuclide decays completely or it is washed out of your body. So that's the difference. You know you're not being exposed to X-rays anymore once they have been turned off. But once a radionuclide is ingested or inhaled, taken into your body, you are continually being irradiated until it goes away one way or the other.
Good.
But no, medical X-rays are not safe.
No, absolutely.
You do get a benefit if you choose to have them, if you need them. So
Yes.
that makes them fundamentally different than something you never even knew happened because you lived next door to an industrial facility that was changing your future without your knowledge.
And that does not mean that the damage that came from that X-ray that you got doesn't continue in your body, right? So that just means that you do know, when the machine of the X-ray that produces the X-ray is turned off, you are no longer exposed. But exposure is not the same as damage.
Okay. Well, that's a good understanding of, it's a cumulative effect is what you're alluding to is the problem where these other incidences are not cumulative. Okay, so we can go on to the next question, and this is for Ian. Some reports indicated that low levels of radiation can cause diseases or adverse health impacts, including cancers, cardiovascular impairments, and other immune systems disorders. But nuclear regulations allow exposures to radiation within certain limits. How are these radiation limits established, and are they protective of the human health and the environment?
Well, good question. There's a great deal of murkiness and grayness around how our current so-called current safety limits are arrived at. They've been around since the end of World War II in the 40s and 50s. And right now, the current legal limit for exposure of a member of the public to radiation is 1 millisievert per year. Now, the question is that safe? Well, I don't think it is. The thing is that to establish a safety limit, you have to determine what is the tolerable amount of radiation that we can receive. And that's a political question. Because at the start of this talk, I showed you that even the tiniest dose of radiation can cause a cancer. There is no safe limit. I'll repeat that. There is no safe limit. The only amount of radiation that we know of that won't result in a cancer is 0 dose. That raises all sorts of questions. Well, where did the limits come from? That's very good. They seem to have emerged from scientific conferences after the war, where people got round at the table and said, well, let's pick a figure of 1 millisievert, because that at that time, back in the 1950s, that was what was thought that the background levels of radiation were. They said, well, that's going to be safe, well, we'll take that. Well, we know now, of course, that background radiation is in fact dangerous. Some very reputable scientists reckon, for example, that it causes 20% of all childhood leukemias. I'll repeat that. That background radiation results in the deaths of children from leukemia, about 20%. Other scientists think it's more like 50%. Some even say it's 100% for childhood leukemia, that is. Well, we don't really know what the exact figure is, but background radiation is dangerous. And in the book that Cindy and I have written, there's a whole appendix on background radiation, 2 appendices, M and N. And one is on the background radiation from man-made radiation, and the other one is from non-man-made radiation. Man-made, by the way, is mostly medical radiation. It's these 2 appendices go on for about 20 pages, so really the best thing to do is read them rather than for us to discuss it. But I'm not answering your question. Are the limits safe? Well, I don't think they are. I think they should be tightened considerably. But here we are right now. What are we going to do about it? Even now, we've seen that the limits that are used for some internal radionuclides are huge, very, very lax indeed. So the whole question about limits to radiation is really up in the air and it's highly unsatisfactory. All I can say is watch this space. Okay, that's not a very good answer, Bill, but it's there isn't a very good answer. I'll finish there.
You're on mute, Bill.
Bill, you're on mute.
Okay, thanks, Ian. That's very interesting, and you're right. There is no science that would say what the levels should or should not be, but 0 is a good number. See, Mary or Cindy, you want to add anything to that? We have a large number of questions from the audience, so we may want to move on to the next question, the last question. And that's for Mary. It's the Deep Geological Repository that was proposed for Yucca Mountain in Nevada was closely scrutinized and heavily criticized before halted several years ago. Mary, can you give us some insights of why this project got halted, or what have we learned from Yucca Mountain?
Yeah, I'm going to keep this short, but there's sort of this ancient idea that putting something into the earth is putting it down there, which we now have a greater photographic understanding of our planet as a sphere. And so it's really in there. And so at Yucca Mountain, putting radioactive waste in there would be putting it literally on top of a magma pocket. That's the biggest reason that the science-based community gathered together to do our best within the very limited regulatory process to halt that program. And I'll just give you the little evidence. First, there's a row of lava cones, the youngest of which is closest to Yucca Mountain, and the row points exactly at where they wanted to put the waste. So like the Hawaiian Islands, there's a single magma pocket, and the Earth's crust is slowly moving, and so a new cone is deposited as the crust moves. And so the idea that there might be like a volcano of radioactive waste actually was not considered to be incredible. Every credible scenario, according to the US EPA, has to be considered. The Environmental Protection Agency, EPA, has to be considered in a environmental impact statement. And they actually do consider a magma eruption through Yucca Mountain. So this was the, I'm sorry, Ian, could you mute, please?
What else to do? They're way overturned.
Ian, could you mute, please? Maybe someone could help. Okay. So the long and the short is this was a terrible site and it had to be stopped. And so it's only been paused, unfortunately, because the courts that we turned to said it was up to Congress. And if Congress gave the program more money, it would restart. If they didn't, it wouldn't. And so it sits there eternally as a maybe right now, which is very unfortunate. But just to tell you how they considered and an example of how science can be manipulated and skewed in ways that are completely non-scientific, the chapter on a volcanic eruption through the waste had lethal levels of radioactivity that would result, but these were not reported in the EPA, in the environmental impact statement. Instead, what was reported was a dose to a person walking around at that time at some point in the future that this eruption might occur, that was lowered by the probability of the eruption occurring in any given year out to 1,000,000 years. So that lowered the dose by 6 orders of magnitude because they were averaging it across that 1,000,000 years. So this is not science. This is not what would happen if, in fact, the magma pocket did erupt. And yet that's what passes in radioactive waste policy as an acceptable thing to the administration at the time that EIS that was accepted, which was the George W. Bush administration. I like to think that other administrations might have given it more care and consideration. So then very briefly, how the project was brought to Congress's attention in a way that helped them to defund it is that we figured out that the largest number of voters, and this is a little different than the consent-based model, but the largest number of voters was the transportation routes, the people living along those routes, and the potential for catastrophic accidents. And again, the federal officials admitted that there would be 5 major accidents involving the release of irradiated fuel, which is lethal levels of radiation to anyone nearby, as in, within a quarter mile is not great. Down in feet and yards, you're pretty much dead. So 5 of those during the course of the time in the United States it would take to move the waste. So, non-controversial that there will be accidents, but they were not publishing the routes for the transportation. So the communities did that. We got access to their computer models and we put in the input information. We didn't publish stuff that would enable a terrorist to plan ahead, but we published the pictures of the ways in which the waste would travel. And we let people in each congressional district know that this was a factor. So I'm going to stop there, but just to say that information is power. People are power. It is important that people who are making the decisions have the information they need to protect themselves. And in this picture, we were protecting the Shoshone people who said that they did not want the waste to come there, but their numbers were very small compared to the numbers along the transportation routes. So we were supporting the people who were most local and supporting good science that said that this location was just rotten, just rotten.
Well, thank you, Mary. That's an important message, that information is power. And people have the ability to have that power. So we need to use it to educate those that are uninformed about the dangers of radioactive releases. So, Bernine, I'm going to turn it over to you to some of the questions from the audience. I know you've been looking at those, and maybe you can decide which ones we need to get answered.
Great, thanks, Bill. We've got a lot of questions in the Q&A, and if people are putting them in the chat, I'm going to stop watching the chat now and look only at the Q&A. We've got a couple that actually were already answered, and I'll revisit them, but I'm going to start with the open questions. The first one actually is Ian back. I'm going to wait till Ian turns his camera on so that we know that he's back. There's a question from Pierre. Pierre asks about the incidence of cancer resulting from radon exposure.
No.
Okay, very good. Thank you, Ian. A question from Pierre about the incidence of cancer resulting from radon exposure as denounced in Quebec by Dr. Amir Kadir. I'm not sure if anyone is familiar with that. If Ian, are you familiar with that?
No, I'm not.
Okay, Pierre, I think we might have to get back to you on that because I don't think our panelists are, it's an international panel. Maybe if you could send us the reference to that, we could ask them to be so generous as to respond. Ian, I'm going to go back to a question for you from Mary Lou. Please comment on whether this is the case. Whereas a single molecule of a chemical that damages chromosomes will damage one area where it interacts with that chromosome, a track of radioactive molecules can damage up to 7 areas of chromosomes. So a very specific and quite technical question. Ian, are you good with that?
I didn't say that.
No, Mary Lou is asking you that. It's a
Well,
question,
I don't know where
it's
she
not an
gets the number
argument.
7 from.
Pardon me?
She quotes the number 7 chromosome.
Yes.
I've got no idea where she gets that from.
Okay, so, all right, so I'm gonna, no comment on that then. Okay.
Right.
So a question from Roger.
Mary had her hand raised for a minute, Bernine.
Pardon me?
Mary had her hand raised.
Oh, I'm sorry. Mary, go to you. I can't.
Well, just a quick comment on radiation damage, not as specific as that question, but external exposure is pure energy. Internal exposure, because it penetrates, the particles just simply bounce off. So internal exposure can be either that pure energy of gamma or not X-rays internally, but gamma rays internally, or it can include alpha and beta particles. Those particles have mass and they have terminal velocity, and we have to analyze them in a different manner than the pure energy ones. And they have the capacity to do things like break chromosomes, which I know that the gamma rays can also, but these are, in general, a much higher level of damage from alpha particles and beta particles in our bodies. So yes, different exposures do different things. And no, it is not a simple matter. And yes, we are all learning a lot about all of this because we have new findings, but I'm not going to take the time on that. But I just want people to hear that it is not simple.
Great. Thanks very much, Mary. That's really helpful. A question from Roger. The industry claims that the atmospheric and water low dose radiation releases at the nuclear power plant are tiny and harmless and don't travel very far. The HHS, that might be a US agency, I'm not familiar with it, recently canceled the National Academy of Sciences study of cancer effects around nuclear power plants because they already know that there are no effects. Cindy or Mary, do you want to comment on that, respond to that?
Yeah, actually, I had asked to answer this question live, and then another question by Dennis Cambly on what about those of us who live downwind from the US government tests, 928 nuclear tests in Nevada. And the reason that I want to answer these questions together is because, yes, Dennis, you are correct. We are all downwind. Some of us are more downwind than others. And again, I go back to what I consider or what I call historic or legacy exposures, right? So we are starting, as I said before, at a deficit. at a potential level of damage that was much higher than we would have had, say, in the 1930s, when this stuff was not as widespread, when radioactivity was not spewed all over the place. And this gets to Roger's question about what do you mean by tiny amounts? I want to pick that apart, and I want to focus on that piece, because there is no tiny amount of radioactivity. There never was. And I think that the studies are showing that repairing damage now, even to tiny amounts of radioactivity, is getting harder and harder to do. And this is because we have been historically exposed. And so I worry that when we talk about limits and setting limits of 1 millisievert or whatever limit is too high anyway, but that with each successive generation, is that limit even going to be, does that limit even need to be lower? Because I don't know how we are. I mean, this is one of the studies that came out of Chernobyl, and it was looking at birds, and it realized that the dose that they were assessing for, a dose in isolation to all other radiation doses, could not have caused the harm they were seeing in the birds. But when they added in that dose from the original Chernobyl explosion and accident, not just the radiation that was lingering in the environment generations later, they understood that what they were seeing was a compounding dose impact. And so that's when they started to talk about historic dose with regard to birds. And I can't think that we're that much more different than birds. Not that birds don't matter, they do. And so all of this is to say, I really feel like when they talk about tiny doses, they're compartmentalizing themselves again. They're compartmentalizing us again, and we can't allow them to do that. We need accountability for the exposures that we as a species and our environment and all of the other species have already suffered, in order to say whether a dose is small or not. And we are working down to the point where there are no small doses anymore. So I just wanted to throw that out there. And I don't know if that answered their questions fully, but I think it's an important point to make in the context of they just keep wanting to use this technology, and they have not accounted for the past damage at all.
Great. Thanks, Cindy. Very helpful. Ian, you wanted to add to that?
Yeah, the questioner alleges that the amounts coming out of nuclear facilities are small. Tiny, he said. Well, that's crazy. That's not the case. The discharges from nuclear facilities in Ontario are, as I said before, extremely large. So that means that people who are living downwind or nearby are going to get large doses. And indeed, I've recommended that people who live within 10 kilometers of nuclear power stations should not, well, if you're a pregnant woman, you shouldn't be living there and should move away. And that people who have gardens shouldn't eat their produce. And that includes honey hives as well. And so it's a serious issue. It's not just a small amount. No, it's not. They're large amounts. We should be worried about the discharges from nuclear facilities in Ontario.
Great. Thanks, Ian. I'm going to go to a couple of the questions that were answered, just so people are aware of them. Cindy answered a question about the distinction between ionizing and non-ionizing radiation. And Cindy gave an excellent response, which I'm going to read, Cindy, so you don't have to say it again. In general, ionizing radiation breaks chemical bonds of molecules, and non-ionizing radiation shakes molecules. And it's important to remember that there can be some crossover between ionizing and non-ionizing radiation. That is an excellent, very succinct response, Cindy. Thanks for that. There was also a question that Cindy answered. Is there evidence that smokers' lung cancer is largely or partially caused by polonium? And Cindy provided a link saying maybe. So we'll include that link in the chat that we'll send out.
Gordon also answered that question in the Q&A. Gordon answered that question as well.
Okay, I don't see Gordon's responses in the Q&A. I only see the panelist responses in the Q&A.
Okay.
So I'll go to back to the open questions. And this is similar to the question that Cindy answered around ionizing, non-ionizing. Can you speak to dental x-rays, mammograms, other x-rays? And we did hear some on this earlier in the first set of questions. I understand mammograms are not used in EU countries. What about, I would say, background radiation, what we eat, breathe, consume internally? Mary, would you like to start with that?
Sure. You know, the CT scan is not well, the disclosure to the patient about CT scans is pretty skimpy, but it's hundreds of times higher. Now, I probably should say more like 100 times higher, but some of the longer series are hundreds of times higher than a single. X-rays today are digital. When I was a kid, they actually had photographic film that was exposed. So X-rays were a lot higher back then. So yes, they are lower today. But CT scans are flowing like water in some hospitals, including where my sister-in-law was, and it really alarms me. That distribution that I showed in the bar chart of my slides, it was based on everybody getting one gray. There's a similar one that I did for what if you got one CT scan. And yeah, it's only a 1% increase, but how many other exposures are you going to have? That's a single exposure. How many do you get over your life? How much disclosure are you getting? Are you making good choices? If you need them, if they're going to save your life, obviously, I recommend it because you can't get cancer after you're dead. But if it's not to save your life, there should be some real thought put into medical choices. Now, briefly on background. People have the idea that background radiation is one number because that's how it's reported by governments, as one number. And that is their construction of what is actually micro variation across the entire planet all the time, because it's not only what is in the rocks and what is in the soil, it's also the radiation coming in from space. Sometimes there's events at great distance that can cause a spike in gamma rays on the Earth. Well beyond the sun. And now we know from sun storms that we're getting in our weather reports that there's a change in what comes to the planet from the sun. So there's constant variation of what we do acknowledge as being far beyond our control. So take that one number. And when I started the job that I had in 1991, the one number was 100 millirems a year was background. Okay.
Translate
The
that.
U.S. Nuclear Regulatory Commission assigns to 100 millirems a year across your lifetime a chance of getting cancer of 1 in 286 people, which is certainly low compared to the current cancer rate, but it's certainly high compared to 1 in a million being sort of more what we all thought low exposures would give us. So background radiation is dangerous. I'm not even going into talking about the risks associated with specific radionuclides that are specific background levels. But then today, they say in the United States, our background level is 600 millirems a year or 6 millisieverts. So why would that happen? Well, it's all that spewing out of radioactivity that we've been doing, and they also incorporated nuclear medicine and medical exposures. And since most people in the population are not getting those, you have to understand that those are enormously high exposures. Plus, it now creates a ceiling or a floor rather for pollution to rise to the 600 millirem or 6 millisievert level a year, and nobody's going to bat an eyelash, which is, again, the perversion of science. So are we talking background, natural background, or are we talking background pre-approved pollution? And I think most of the time it's pre-approved pollution. Now, Ian, you've been waiting and I'll cede to you.
No. That's fine. The whole issue of background radiation is a vexed topic, and it's dealt with in our book, as I said, and We could have a whole webinar just on background radiation. Easy peasy. Hours, days. So,
Lifetimes.
next time. The key takeaway is background radiation is dangerous, and don't let them fool you with it. Full stop.
Great. Thanks, Saul. We are at our estimated finish time. I'm going to ask the panelists if they're able to stay on for another 15 minutes, and we'll work through a few remaining questions. Is that good? No pressure? But if it's good,
I have to go.
okay. All right.
Well, I'll explain to people that I'm talking from London, England, and our family here is having dinner. And
Okay.
making signs at me that I should.
All right.
Join them.
Well, thanks very much for joining us, Ian.
No,
And
my pleasure. And I hope you guys manage to
Thank the other panelists
overturn
as
this
well.
proposal by.
It's been a
your,
very
there
interesting
you
session.
go,
I really appreciate the information that
South
you're.
Rift doesn't deserve this. So all the very best for the future, okay?
great. Thanks very
Bye.
much, Ian.
Okay, bye now.
Bill, I think you were trying to say something while Ian
Well,
was
I
saying.
was just saying, I wanted to thank Ian, but also Sydney and Mary for the information they're sharing. It's been very educational for me, and I'm sure for a large number of the attendees. And we really appreciate the time. And I know it takes time to make these presentations and worthwhile. And so it's just not a question you come here and you make your presentation. It means you've done a lot of work prior to this. So I really do appreciate that. And Bernine, let's get on with the rest of the questions so we don't hold the crowd too long.
All right. Thanks very much, Bill. So a question, Bill Gates' new plan to build nuclear plants to run with weapons grade plutonium, health impacts, and you can answer this specific to Bill Gates's purported reactor design or to next generation small modular reactors in general, however you'd like to approach it. Cindy and then Mary, perhaps.
So I'll just start by saying that every time somebody wants to build one of these reactors or wants to drag one out of its grave or wants to keep it running, they're not looking at the front end of the fuel cycle. They don't like to look at the uranium mining piece. They don't want to look at the uranium mining piece because in the United States, we have just completely mistreated the people at the front end of the fuel cycle. Many, if not all, most, and this is a worldwide thing, are indigenous people. So in America, it's Native Americans. And so here we are. On the one hand, you have the Biden initiative for environmental justice and considering climate change in the guise of environmental justice. At the same time, they're just passing legislation to make NRC a promotional agency again. And they're continuing nuclear reactors, which is going to require uranium mining. And we just have Pinyon Plain Mine opening up out in the Southwest. And so again, it's a 30,000 foot issue, but when you're using an energy source like this and you see the SMRs that they want to build and you see these other ones that they want to build, they're going to have the fuel source from somewhere. And the place where they get it in the United States is from in and around Native American lands that they have never, again, been accountable for the damage that they've caused from the beginning. And part of me thinks that we will never see a new generation of nuclear reactors because I suspect that the reason that they want nuclear technology to persist is weapons. So they have all these pie in the sky designs and SMRs, which are paper nukes, and all of these other bits and pieces that they're trying to continue. But as far as technology goes, I do not think that we would be so forceful about a technology that is too expensive to address climate change any more efficiently, less efficiently. It will address it less efficiently, according to IPCC report 2022, than either wind or solar. It's a lot more money. and it's a lot more dangerous all along the fuel chain. And so when you have an energy source like this, and you're saying you want to use it to produce energy, but it's not really suited to that, you have to look for an ulterior motive. And I think the ulterior motive is probably nuclear weapons. And I am not the first, and I will not be the last person to say that. Alfred Meyer has done a whole lot of work on this stateside. And I'm sure that there are some folks in Canada who have also looked at this issue, but I'm gonna let Mary take it.
Great, thanks.
Okay, so real quick, we're getting close to our new time. If you don't use uranium as fuel, what you gonna use? Well, the claim is they're gonna use nuclear waste. However, that and the recent legislation that has just passed in Washington, D.C., puts the United States on a track that it decided to not take back in the Ford administration, which is like, 40, 50 years ago now, which has to do with the separation of plutonium. Now, there's been a fair amount of that going on in Canada and in the UK and in France and in Russia. Those are the big reprocessing nations that other countries sent their waste to get the plutonium separated. Lord only knows why you'd want to separate plutonium, especially since all of the great minds that put their heads together about what to do with dismantled nuclear weapons, which, oh yes, by the way, we took a lot of them apart. Hallelujah. And what do you do with the plutonium from a dismantled nuclear weapon? Well, you make it just as radioactive as it would have been if it had stayed in the waste. So why aren't we leaving plutonium in the waste? Why would anyone decide to separate the plutonium out of commercial waste? Well, we've got people with names who have become hallowed, which I don't understand. He's not a particularly great leader, Bill Gates. I don't understand why they suddenly think he understands energy policy when all he really understands is code. So why are we following someone who is not in his lane towards separation of plutonium, which is the most environmentally horrific part of the nuclear activity ever? You just look at these huge, huge swaths of contamination that cannot and will not ever be cleaned up. You look at the cancer rates in the areas, Cumbria is well documented. You look at Mayak region in Russia. You look at cancer rates of children on the beach in France near the big La Hague facility there. These are enormously horrible things and sites. So the United States actually decided not to do it because we didn't want to contribute to the proliferation of nuclear weapons around the world. But we also saved ourselves from that really enormous additional impact over and above the 120 nuclear power plants that we built. So, this whole idea that, oh, we're going to use the waste. Well, you can't use the waste unless you go down the road of reprocessing and separating it apart. You can't make fuels out of the actual fuel rods, which is what that waste is today. And that's what the DGR is considering. In Canada, it's called a DGR. In the United States, we called it Yucca Mountain, but it's got a big, huge clutch in on it. So right now, there's enormous amounts of this material that are just sitting where it was generated or in some other location that they've moved it to. But it's like having a plumbing problem in a skyscraper. How and why would you start continuing to rent offices in that skyscraper when none of the toilets flush, when it's just all full of waste backing up? And that is the picture of nuclear energy in North America. Okay. So, there's all kinds of answers you can come up with, but it's sort of like that background webinar. It could go on for the rest of our lives. And quite frankly, that's a happy story. I always say to the women in the restroom now, there are other women working on nuclear waste policy. And when we're at a big meeting and they're in the restroom, I say, hey, if this conversation goes on for the next, 240,000 years, 10 half-lives of plutonium, we're doing great. We're doing great. So yeah, we have to put our attention on it. We should not feel defeated because there is not an answer. We should only feel defeated when the waste itself goes to a less safe, less secure, more leaky situation than it is now. And all of us need to keep pulling it back from that leaky, insecure, dangerous place. And unfortunately, my friend Kathleen Sullivan is correct. We've created a new baby and we're just plain going to have to take care of it.
Great, thanks. Mary, that's such a great note. I almost want to end there, but instead I'm going to try to squeeze in two more questions. One is, I'm going to combine a question from Renee about the danger of transportation of enriched uranium with a question from Roger about radiation release from waste storage containers. And I'm wondering, Mary, maybe if you could start and talk about the radiation effects of high-level radioactive waste transportation.
Oh, come on. Let me talk about storage containers and transportation.
Okay, you can do that.
Okay, because this has a really important point that you asked me to bone up on, which is what do you do to get the waste out of one container into another?
Right.
And in many places, you have to do that before you can transport the waste. And at Yucca Mountain and potentially at a DGR, since we don't really know what the DGR is going to look like or anything about its design, we don't know what the waste acceptance criteria will be. But any permanent place for waste is going to have a waste handling section. So there's potentially recontaining at the site, and some will also have to be recontained at the destination. And some destinations have really strict requirements that's going to add a lot of handling at that site. So going to it, there's basically two ways that are currently talked about, and maybe someone brilliant is going to come up with another option because both of these are pretty bad. The first way to transfer waste into a container that you can move it or into a container that you can then put it in a permanent place is to have a fuel pool. And in the United States, the brilliant people who are handling the dismantlement of reactors are taking those fuel pools out. So we have dry sites where waste is sitting in containers. And to get to that question about radioactivity in that container, yes, there's shielding to reduce it. Yes, the waste is in a welded container, so there's not radioactive liquid or solid leaking out. But yes, the gamma rays, in some cases X-rays, depending on the materials involved, and definitely the neutrons are still coming out of that container. So it's not contamination, but it is radiation. And in many locations, they've shielded around the sides with earth, but the radiation gets focused, goes up and bounces off any clouds and comes back down as shine. So virtually every waste storage site has the potential for exposure. So now let's say they can transfer in a pool, they put the container down into the pool, they let all the temperatures change, and then they think somehow they're going to open it and move it. Well, those canisters, they don't open. They just recontainerize them in some models. Other models, they think they're going to open those canisters. Good luck. The times that that's been tried, it went really bad. So this is kind of like a fantasy team that's going to do this. Now, the other option is to have what's called a hot cell, which is essentially a sealed building that has robotics inside, and they open containers and transfer waste, and they have to have since they don't have the water to be the atmosphere, they have to have a neutral gas because irradiated fuel will spontaneously combust if it's exposed to air. So I was talking to several people about the hot cell model because I don't have any background in that. I'm talking to people who have decades of work on the Yucca Mountain proposal because there was a hot cell idea there for a while. It got canceled. The reason it got canceled is because the buildup of contamination from handling the bare fuel is sufficient that after a couple days you have to shut it down and clean it out because they have not only the potential for fires if there's air leak, but uncontained criticality because there's so much stuff that just drops off and can get then pulled into the ventilation system. So criticality is when plutonium or fissile uranium starts splitting. And if it's uncontained, well, you've got a real problem. It's like most likely not a bomb. It's most likely like a reactor with no containment system and no cooling. And suddenly you have a crisis that you don't know how to shut down. So that's why they canceled the idea of a hot cell at Yucca Mountain and went to the idea that they would have pools there. So Yucca Mountain's not happening. The DGR has not happened yet, but the DGR that we have heard a little bit about would have hot cells. So very high worker exposures, very high potential for releases, especially if there's a criticality concern that's not tracked on a daily basis. And what did we say about the DGR? It would have a beginning, but in the plan, it has no end. It will continue to operate as long as irradiated fuel is generated in Canada. So this is a commitment to preventing criticality on a day-by-day basis for the rest of known nuclear history. And we knew that about putting the waste in a permanent place, but this is an operation, and that's different. So is there radioactivity associated with a hot cell? Absolutely. There's the same gamma rays that can come through virtually any level of shielding to some amount. And certainly if you have a fire or a criticality, we're talking about public having to shelter in place, people being evacuated. I mean, it's not pretty. It is totally not pretty.
Great. Cindy, did you want to add to that very excellent answer by Mary?
No, I mean, except to maybe say one thing, and that is that, you know, I kind of look at all of this sort of, especially the waste disposal issue, just sort of, again, taking the 30,000-foot view. And I use disposal in quotes, so storage. Yeah. So I regard it as a way for them to sort of get rid of the problem from their eyes so that they can generate more of the problem, rather than using it as a stopgap to stop making it, to get rid of this technology altogether. So it's almost like they can say, oh, well, if people accept a solution again in quotes, to the issue, to this radioactive waste issue, then we can go ahead, and that's our imprimatur, that's our open door to go ahead and continue using the technology and create more of this problem. And so it's, again, the accountability question. There's no accountability for these folks from beginning to end. And that's the problem with dealing with the nuclear waste problem while they are still making it. Because what they see as a solution is not a solution. What they see as a solution is actually just more exposures to the environment and to human beings and to animals.
Great. Thanks very much. I'm going to hand it back to you, Bill. We do still have a few questions. A couple of them I know we can send out a link to respond to, but I think we're at the end of our time. So thanks very much, Mary and Cindy, and back to you, Bill. Your mic is off, Bill.
Again, I want to thank everybody, Bernane, Anya, and the panelists, Cindy and Mary and Ian, for putting on a excellent presentations and loads of information, which I'm sure we can all digest. But just thank you for taking the time to do this, and I hope that we can do this again sometime. So thank you. So with that, I guess, Bernane, will end the session, and we'll see you again. Bye-bye.